Hello everyone, welcome to the video lecture 5 of module 5 linear algebra. In this lecture we will discuss about eigenvalues and eigenvectors of a matrix. That is, if we have given a matrix, then we will see how we can find its eigenvalues and corresponding eigenvectors. First of all, what eigenvalues and eigenvectors are. So, let A be a square matrix, then a scalar lambda is called an eigenvalue of A if there exists a non-zero column matrix X such that Ax equal to lambda x. That is, if we multiply matrix A with the column matrix X, we should get a scalar multiple of X. And note that here X is a non-zero vector. It is important. The number lambda is called eigenvalue of A and X is called the eigenvector of A corresponding to the eigenvalue lambda. Now, to find the eigenvalues of the matrix A, just consider this. Ax equal to lambda x can be written as Ax minus lambda x equal to 0, and we can write x as I into x, where identity matrix, so that A minus lambda I x equal to 0. Now, next, to find eigenvalues, we consider the determinant of matrix A minus lambda I and equate it to 0. The roots of equation determinant A minus lambda I equal to 0 are nothing but the eigenvalues of A. So here this equation is called the characteristic equation of matrix A, and roots of characteristic equation are called characteristic roots or eigenvalues or latent roots of A. Now let's consider a second order matrix A equal to A, B, C, D. Here suppose we have to find the characteristic roots or eigenvalues of this matrix. So we have to solve the characteristic equation and find the roots. So first we'll write the equation determinant A minus lambda I equal to 0, and then substitute for A and I. I is identity matrix of order 2 here. So determinant of A, which is A, B, C, D, the matrix, minus lambda times identity matrix equal to 0. That is determinant of matrix A minus lambda, B minus 0, C minus 0, D minus lambda. That implies determinant of A minus lambda, B, C, D minus lambda equal to 0. Now expand the determinant. It is A minus lambda into D minus lambda minus BC equal to 0. Or we can multiply and write AD minus D lambda minus A lambda minus plus lambda square minus BC equal to 0. Or we can write lambda square minus lambda, here coefficient is minus of A plus D, plus constant term AD minus BC equal to 0. Now here AD minus BC is nothing but determinant of matrix A. Determinant of matrix A is AD minus BC. So we can write it in the form lambda square minus A plus D lambda plus determinant of A equal to 0. So for a second order matrix, the characteristic equation is lambda square minus A plus D lambda plus determinant of A equal to 0. Here A plus D, sum of the principal diagonal elements of A here, and then we have third term determinant. Similarly, for a third order matrix, A equal to A1 B1 C1, A2 B2 C2, A3 B3 C3, we can prove that the characteristic equation is lambda cube minus A1 plus B2 plus C3 lambda square plus sum of minus of A1 comma B2 and C3 lambda minus determinant of A equal to 0. Here just note this, lambda square coefficient is sum of principal diagonal elements of A, that is A1 plus B2 plus C3. And what do you mean by minors of A1, B2, C3? So minor of A1 is the determinant obtained by deleting the row and column containing A1. So that is minor of A1 is B2 C3 minus C2 B3. Similarly, minor of B2 is just delete the row and column containing B2. So the determinant is A1 C3 minus C1 A3. Similarly, the minor of C3 is A1 B2 minus B1 A2. And find the determinant, substitute, we'll get the 3 roots for this cubic equation. So for a third order matrix there will be 3 eigenvalues. Now let's go through some problems. Problem number 1 is find the eigenvalues and eigenvectors of the matrix 1, 2, 2, 4. So first let's name the matrix. So call it as A. So A is equal to 1, 2, 2, 4. Then first we have to write down the characteristic equation and we have to solve the characteristic equation to find the eigenvalues. So the characteristic equation is determinant of A minus lambda I equal to 0. That is determinant of 1 minus lambda 2, 4 minus lambda equal to 0. Here note that the determinant is just equal to A with the lambda subtracted from each entry on the main diagonal. Next we write the formula now, that is characteristic equation is lambda square minus sum of principal diagonal elements, that is 1 plus 4 times lambda plus determinant of A equal to 0. Now determinant of A is 1 into 4 minus 2 into 2, that is 0. Then we will get lambda square minus 5 lambda plus 0 equal to 0. Now find the roots of this equation. We can write lambda common, we can take outside lambda into lambda minus 5 equal to 0, or we have the roots are 0 and 5. The roots of this equation, the characteristic equation, is nothing but eigenvalues. So we have the eigenvalues are 0 and 5. Next, to find eigenvectors, suppose capital X equal to x, y, this column matrix be the eigenvector of A corresponding to the eigenvalue lambda. Then by definition eigenvector x satisfies the equation Ax equal to lambda x, or we can write Ax minus lambda I times x equal to 0. So substitute for A minus lambda I and x, multiply 1 minus lambda x plus 2y equal to 0, 2x plus 4 minus lambda y equal to 0. So eigenvectors of A can be determined by solving this homogeneous system of equations for each eigenvalue lambda. So first let's take lambda equal to, or first eigenvalue we have 0. We have two eigenvalues 0 and 5. So first take lambda equal to 0. The equation will be 1 minus 0x, that is x plus 2y equal to 0. The second equation will be 2x plus 4y equal to 0. That is, here both the equations are same. So x plus 2y equal to 0, or we can write x equal to minus 2y. So we can take any value for x except x equal to 0, or for any value for y except 0. We cannot take simultaneously 0 because eigenvector is a non-zero vector. So x and y cannot be 0 simultaneously. Suppose I take x equal to 2, then 2 equal to minus 2y, or y equals to minus 1. So the eigenvector corresponding to the eigenvalue 0, here we have x1 equal to 2 minus 1. Next we will take the second case, lambda equal to 5 in the homogeneous equations. So putting lambda equal to 5, we get minus 4x plus 2y equal to 0 and 2x minus y equal to 0. The first equation takes this form and second equation is 2x minus y equal to 0, or we can write 2x equal to y. Both the equations give same, 2x equal to y. Now to find x2 eigenvector, we take x equal to 1. If x is 1, y is equal to 2 into 1, 2. So the eigenvector is x2 is 1, 2, corresponding to the eigenvalue lambda equal to 5. So eigenvalues are 0 and 5 and the corresponding eigenvectors are x1 equal to 2 column matrix 2 minus 1, or you can write row matrix 2 minus 1 transpose and 1 2 transpose respectively. Now let's take the second problem. Find the eigenvalues and eigenvectors of the matrix 1 1 3 1 5 1 3 1 1. So first call it as A and then write the characteristic equation, determinant of A minus lambda I equal to 0. That is, from the diagonal entry subtract lambda, we get 1 minus lambda, 5 minus lambda, 1 minus lambda, and remaining entries write as it is. So we can write lambda cube minus, here second term containing lambda square, coefficient is to write the sum of principal diagonal elements of A, that is 1 plus 5 plus 1, plus next we have term containing lambda, its coefficient is sum of minors of 1 5 1. Okay, so what is the minor of 1? It is the determinant obtained by deleting the row and column containing 1, that is, it is determinant of this 5 into 1 minus 1 into 1, that is 5 minus 1 4. Similarly, the minor of 5 is 1 into 1 minus 3 into 3, that is 1 minus 9 minus 8. Then we have minor of 1 is 1 into 5 minus 1 into 1, 4 it is. Then minus determinant of A equal to 0. So find the determinant of A and substitute. So here lambda cube minus 1 plus 5 plus 1, that is 7 lambda square, plus this is 0 0 lambda, minus determinant of A minus 36. You can calculate using calculator and then substitute and find the roots of this cubic equation. We will get 3 roots and the roots are nothing but eigenvalues of the matrix. So the eigenvalues are minus 2 3 6. The roots of this equation are minus 2 3 6 and these are the eigenvalues. Next, to get the eigenvectors, we consider the column matrix x y z. Suppose this is the eigenvector of A, then we have Ax equal to lambda x, or we can write A minus lambda I x equal to 0, or this is A minus lambda I into x equal to 0. Multiply and write, we get this set of or system of homogeneous equations. 1 minus lambda x plus y plus 3z equal to 0, x plus minus plus 5 minus lambda y plus z equal to 0. Third equation is 3x plus y plus 1 minus lambda z equal to 0. Now substitute the three values of eigenvalues. Okay, lambda 1, lambda 2, lambda 3. Here in place of lambda we'll get solving, we'll get 3 eigenvectors. So let's start with our first eigenvalue. Suppose lambda equals to minus 2, then the first equation becomes 1 minus minus 2x plus y plus 3z equal to 0. That is 3x plus y plus 3z equal to 0. Second equation becomes x plus 7y plus z equal to 0. And third equation is now 3x plus y plus 3z equal to 0. So we get these three equations by taking lambda 1 equal to minus 2 in the homogeneous system of equations. Now take any two equations and solve it, and I am going to take first two equations. So I am going to multiply the second equation by 3 and subtract one from the other. So first equation is 3x plus y plus 3z equal to 0, and multiplying the second equation by 3 we'll get a 3x plus 21y plus 3z equal to 0. Then subtract one from the other, we'll get a 20y equal to 0 or y equals to 0. If I take y equal to 0 in the first equation, we get 3x plus 3z equal to 0 or x plus z equal to 0 or z equal to minus x. So our eigenvector will be, so here x, y, z, y is equal to 0, take x equal to 1. If I take x equal to 1, z will be minus 1. So x is 1, y is 0, z is minus 1. This is the eigenvector corresponding to lambda 1 equal to minus 2. Next, we'll take the second eigenvalue lambda equal to 3 in the homogeneous system of equations, and we get these three equations. Here multiply the second equation by 2, so it will be 2x plus 4y plus 2z equal to 0. Then add these two equations, then multiplying by 2, then adding, will get y plus 4y, that is 5y plus 5z equal to 0. So here this will be 0. If I multiply by 2 and add, this will be 0. And here y plus 4y, 3z plus 2z, that is 5y plus 5z equal to 0 or y plus z equal to 0, y equals to minus z. Then take y equal to, if I take y equal to minus 1, then that will be plus 1. If y is minus 1, z equal to plus 1, from the first equation we will get minus 2x minus 1 plus 3 equal to 0, or solving for x we get x equal to 1. So this is the eigenvector corresponding to eigenvalue lambda equal to 3. Next, third case, take the eigenvalue lambda equal to 6. In the three equations we will get these three equations. So if I add the first two equations, here we can note that plus y, here we have minus y. So adding, will get minus 4x plus 4z equal to 0 or minus x plus z equal to 0 or z equal to plus x. So if I take x equal to 1, then z will be 1 only from this relation. When x is 1 and z is 1, y equals to, we can solve for y from the first equation, or you can use the second equation, solve for y. When x is 1, y is 1, so 1 plus 1 minus y equal to 0, that is we will get y equal to 2. So the eigenvector corresponding to eigenvalue 6 is x3 equal to 1, 2, 1. So we have eigenvalues are minus 2, 3, 6, and the corresponding eigenvectors are this column vector 1, 0, minus 1, or the row matrix transpose 1, 0, minus 1, and 1, minus 1, 1 transpose, 1, 2, 1 transpose respectively. Next question. Find the eigenvalues and eigenvectors of the matrix 8, minus 6, 2, minus 6, 7, minus 4, 2, minus 4, 3. Here again, first start with the characteristic equation. Find this determinant a minus lambda I equal to 0. So determinant a minus lambda is determinant of 8 minus, along the diagonal we have to write 8 minus lambda, 7 minus lambda, 3 minus lambda. Remaining entries write as it is, equate it to 0. Then use this lambda cube minus coefficient 8 plus this, entries on the diagonal, principal diagonal entries, sum of the principal diagonal entries of matrix C, 8 plus 7 plus 3 lambda square plus sum of the minus of coefficients or diagonal entries 8, 7, 3. So 8 minor is 7 into 3 minus 4 into minus 4, that is 21 minus 16, 5 it is. Then we have minor of 7 is 8 into 3 minus 2 into 2, that is 24 minus 4, 20. Then minor of 3 is 8 into 7 minus 6 into 6, that is 56 minus 36, 20 into lambda minus determinant of A equal to 0. Find the determinant of the matrix A and substitute lambda cube minus 18 lambda square plus 45 lambda minus 0 equal to 0. Here determinant of A is 0. So find the three roots. The roots are 0, 3 and 15. So the roots of characteristic equations are eigenvalues. So the eigenvalues are 0, 3 and 15. Next, to find the eigenvectors, consider the matrix, column matrix x, y, z, eigenvector. If it is eigenvector, then we have Ax equal to lambda x, or it satisfies the equation A minus lambda I x equal to 0. Substitute for A minus lambda I and x and multiply, we will get these three equations, homogeneous equations. So then we substitute the three values of lambda and we get three eigenvectors corresponding to the values of three eigenvalues. So first case, we take lambda equal to 0, the homogeneous equations reduced to these three equations. Now solve for x, y, z. I'll take the first two equations, multiply the first equation by 2 and then add the two equations. So this will be eliminated. So 16x minus 12y plus 4z equal to 0, minus 6x plus 7y minus 4z equal to 0, then add, we'll get, so here 16x minus 6x, 10x, minus 12y plus 7y is minus 5y. Adding, we'll get this, or we can write y equal to 2x. So the eigenvector, when x is 1, from this, when x is 1, y equals to 2, and put x equal to 1, y equal to 2 in the first equation. So 8 into 1 minus 6 into 2 plus 2z equal to 0. Then solve for z, we'll get z equal to 2. So the eigenvector corresponding to lambda equal to 0 is 1, 2, 2. Column matrix 1, 2, 2. Then we have second case, lambda is 3. Substituting in the homogeneous equations, three equations become 5x minus 6y plus 2z equal to 0, minus 6x plus 4y minus 4z equal to 0, 2x minus 4y equals to 0. Now from the last equation, here we can see 2x is 4y, or x can be written as 2y. So if I take x equal to 1, then y will be 1 by 2. So I'll get y equal to half, fraction. So try to avoid fractions. So I'll take x equal to 2 so that y will be 1 only. So x2, y1. Then from the first equation, solve for z. Put x equal to 2 and y equal to 1. So 10 minus 6, 4 plus 2z equal to 0, or 2z is minus 4, z equal to minus 2. So this will be the eigenvector corresponding to the eigenvalue lambda equal to 3. Then third case, put lambda equal to 15 in the three equations. So the equations reduced to these three equations: minus 7x minus 6y plus 2z equal to 0, minus 6x minus 8y minus 4z equal to 0, 2x minus 4y minus 12z equal to 0. So here first equation we can see here, multiply by 2, then add the two equations. So this will be minus 14x minus 12y plus 4z equal to 0. Then adding, this will be eliminated. Okay, so minus 14x minus 6x, we have minus 14x minus 6x is minus 20x. Then we have minus 12y minus 8y is minus 20y plus 4z minus 4z, we have 0. So we have from this y equal to minus 6. So when x is 2, okay, y is minus 2, because if I take 1 and minus 1, then that will get half. You can check this. Okay, so I'll take x equal to 2, y equal to minus 2, and putting here in the first equation, we will get the value of z as 1. So these are the three eigenvectors corresponding to the eigenvalues 0, 3, 15. Next problem, find the eigenvalues and eigenvectors of the matrix 6 minus 2 2 minus 2 3 minus 1 2 minus 1 3. So here call it as A and find the characteristic equation determinant A minus lambda I equal to 0, or this is nothing but 6 minus lambda, 3 minus lambda, 3 minus lambda along the diagonal, and remaining entries minus 2 2 minus 2 minus 1 2 minus 1, right, as it is. So then we can expand it as, or we can write it as lambda cube minus, so here 6 plus 3 lambda square plus minor of 6 is 3 into 3 minus 1, that is 18. 9 minus 1 8 it is. Then we have minor of 3, we have 6 into 3 minus 2 into 2, it is 14, and minor of 3 is 6 into 3 minus 2 into 2, or minus 2 into minus 2 will get 14 into lambda minus determinant of A equal to 0, that is lambda cube minus 12 lambda square plus 36 lambda, and determinant of A is 32. Substituting will get this, and solve. The roots are 2, 2 and 8. Actually here we'll use, if you use calculator, we'll get the only two roots, 2 and 8, and to get the repeated root 2, okay, you can use this property. The sum of eigenvalues of a matrix is the sum of principal diagonal elements. So here using calculator we get 2 and 8. So the sum of the eigenvalues should be sum of principal diagonal elements, that it should be 6 plus 3 plus 3, that is 12. The sum of eigenvalues should be 12. So if we get 8 plus 2, to get the third eigenvalue, we use this property, that is sum of the eigenvalues is equal to 12, so that the repeated root must be 2, not 8. So we have 2, 2, 8 are the eigenvalues. Next, write the homogeneous equation to find the eigenvector. Okay, we do the same. So here start with the eigenvector, and then substitute for A minus lambda I and x capital X multiply, we will get this 6 minus lambda x minus 2y plus 2z equal to 0, minus 2x plus 3 minus lambda y minus z equal to 0, 2 into x minus y plus 3 minus lambda z equal to 0. So first take the eigenvalue 2 here. If I take lambda equal to 2, 4x minus 2y plus 2z equal to 0. Second equation will be minus 2x plus y minus z equal to 0. Third equation will be 2x minus y plus z equal to 0. That is, we can see here, taking lambda equal to 2, we get these three equations, and we can observe here all the equations are one and the same. There is actually only one equation. These all equations are same. So we cannot apply the previous method. So here we take one of the variables as 0 and try to express the other two variables in a relation. So take y equal to 0, then we have 4x equal to 2z or z equal to minus 2x. So in the eigenvector xyz, we take y equal to 0, and when z is equal to, or when x is 1, if we take x equal to 1, z will be minus 2. So this will be the eigenvector corresponding to the root or eigenvalue 2. So one more eigenvector corresponding to the root or eigenvalue 2, we take the equations, same one equation we have, and we take now z equal to 0. Okay, instead of y equal to 0, taking y equal to 0, we have got one eigenvector. Now take z equal to 0. In the equation we get 2x equal to y equal to 2x. So in the eigenvector, z coordinate, z value is 0, and when x is 1, y will be 2. So x2 is 1 2 0, the eigenvector corresponding to the root lambda equal to 2. Next we have, okay, taking lambda equal to 8, we get these three equations. So in the homogeneous system of equations, in the previous slide, just take lambda equal to 8, we will get these three equations. Now take the first two equations and solve for x, y, z. So here we can see, we can subtract one from the other, we will get the, so here minus 2y minus minus 5y, that is 3y. Then 2z minus z plus 3z, it is equal to 0. Or we can write z equal to minus y. Okay, here z equal to minus y. So when z is equal to 1, if I take z equal to 1, y will be minus 1, and substitute y equal to minus 1, z equal to 1 in the first equation, we will get x equal to 2. So this is the x3 equal to 2 minus 1 1 is the eigenvector corresponding to lambda equal to 8. Okay, so we have eigenvalues are 2, 2, 8, and the corresponding eigenvectors are these three matrices. Thank you.